In this video, I'll consider another regression pitfall to look out for, and that is autocorrelation. So autocorrelation, or serial correlation, occurs when the regression model residuals violate their independence assumption because they're highly dependent across time. And this can occur when our data has been collected over time, yet the model fails to account for any strong time trends. So this is a whole topic unto itself, time series analysis and forecasting. And so I can just touch very lightly on this topic here because sometimes if we find an autocorrelation problem, we can actually solve that problem with some very simple ideas. But in more complicated examples, it is going to be necessary to go into a little more depth with specialized time series techniques. But let's see how we can detect autocorrelation, and at least for this example that I'll show, how we can solve that particular pitfall. So I've got some economic data here, and let's just take a quick look at the data. There's quite a lot of variables here. These are economic, macroeconomic time series data for years from 1959 up to 2010, and these are different types of time series to do with various indicators about the economy. And so there's a few preliminary calculations that are done here, so I'll just quickly do those. And then here's our first model that we're trying, and so this particular model is based on various economic theories. And if I fit the model and summarize it, everything looks fine, and there's not necessarily anything to worry about here. Yet, if I look at a plot of the residuals, we can immediately see that there's a bit of an issue. Okay, I'm plotting the residuals here over time, and ideally what this plot should look like is just a random scatter of points. There shouldn't be any pattern to these points. Yet we can see, we can almost trace the residuals. One residual is very close to the previous residual, and then the next residual, so they follow each other much more closely than they would if they were just completely random. So this is a clear sign that the independence assumption has been violated, and if we were to try and use this model, it's going to be based on a false assumption. We're assuming independence. We don't have independence, and so any conclusions we try and draw from this fitted model are going to be erroneous. So what to do? So it turns out that if we use first differenced data, then we can actually remove this autocorrelation that's apparent in the residuals. So let me do that. Just as with the previous video, I briefly mentioned that there were numerical methods for assessing non-constant variance, and similarly there's numerical methods for assessing autocorrelation in the residuals, and I'm not going to dwell on those here, but that's what all this other code is. So I'm just going to skip to where we can look at the first difference data. So there's various other things that we can try here. Here we're including a lag response as a predictor, but I want to skip to the model that uses the first differenced data. Okay, so here it is, and I'm hoping that all this code's going to work and that I haven't missed any steps in between. So I guess we'll find out. Okay, it didn't find lag UNR, so let me go back and find out where I defined lag UNR. There it is. Okay, and let's go back to here. Okay, and okay, I think we're okay. Okay, so this model 3 here is my model with first differenced data. Okay, and again, if we just look at the output, we can't really tell whether everything is okay. So instead, what I want to do is I want to look at the residuals, and let's look at the scatter plot. Okay, so I managed to get the code to work. Okay, great. So now if we compare these two plots, this was the plot for the model that I started off with, clear evidence of autocorrelation, and here's the corresponding plot for this new model that uses first differenced data. Okay, not as much sign of an autocorrelation problem here. There's perhaps still a little bit of funkiness going on, but I'm not overly concerned here. It's certainly better than it was, and for most intents and purposes it's good enough. So that's just a very quick introduction to the issue, which is autocorrelation. It's where if we were to look at the residuals plotted against time, there's a lack of independence because the residuals are tracking one another much more closely than they would if they were completely random and independent. And sometimes we can employ time series methods to fix up that problem. And in this case, we used what's known as a first differenced model to correct that problem. I'm not going to worry too much about going into any details on exactly what this model is. That's not what my focus is here. My focus is just illustrating that we have methods of correcting a model that's deficient in some way. For example, it doesn't satisfy the independence assumption, and the fixed up model does satisfy the independence assumption. More broadly speaking, this is another regression pitfall to look out for. So in the previous video we considered a case where the constant variance assumption was in jeopardy, and in this video we looked at an example where the independence assumption was in jeopardy. In the next video we'll consider another type of pitfall that we should look out for, and that's where we have something called multicollinearity, which is where there's very high correlation between some of the predictors and it results in unstable, unsatisfactory models.